Hello, everyone. This is Richie, K2KNB, and this is a discussion of cables and connectors. And it's been something that I just found to be very interesting, and I wanted to pass on information of interest to you, and we'll explain why. But first thing, I wanted to start with two different types of circuits. You have a DC circuit here, direct current. And by the way, the wavelength of a DC circuit is 0. There is no wavelength in a DC circuit. And the only thing that's involved in a DC circuit is basically resistance. And this item here is called a capacitor. And this is a symbol, obviously, for a capacitor. A capacitor stores electrical charge for use of to smooth out if there's an interruption, a burp, or as you notice, many times you shut something off and it doesn't really shut off. You can see that the capacitor continues to discharge until it's fully discharged. And DC circuit, very simple. On the other hand, an AC circuit, look what's happening here at the capacitor. It's charging, it's discharging, charging and discharging. And you notice that a lot of the voltage that would be going down this line is diminished as it would get to the light bulb. What's diminishing it? Well, resistance, but other things. But I do want to point out first, here's an inductor. An inductor is something that happens in a coil of wire. And if I increase this inductance, look what happens to the light bulb. All right, something to be aware of. On the other hand, if I increase the voltage, the frequency, light bulb begins to flash, but there's such an exchange here, we've almost shut off the voltage heading towards the light bulb. So these are the kinds of things that I want you to remember. Frequency is extremely important in what we're talking about. And what I ultimately want you to understand is what you're seeing here is actually what goes through a coaxial cable. Instead of a light bulb, at some point we would have an antenna. Let me see if I can shut this correctly. Okay, so now here we have our cables and connectors. And by the way, that particular simulation is from PHET, which is from the Colorado University. You can look them up. They have some great simulations, great things for you in the kids. So let me get into why this is important. Well, ham radio operators will spend a fair amount of money on a transmitter. They'll maybe buy a decent antenna, but at the very least, they'll try to get their antenna up and working. This transmitter is adding power. This antenna is either giving you the same amount of power that it's getting or adding to it through something called gain. However, when you have coaxial cable and all of the connectors that are involved, you will always lose power. There is nothing that you can do to stop that. You will always lose something in your coaxial cable. And the question is why and how much are you willing to lose? Now, ham radio operators, as I said, will spend money on the transmitter, spend money on an antenna, and then they'll run to a ham fest or a flea market and they'll pick up some cable. They need to save on the cable. This cable may work perfectly, possible, but I want to point out that this little area over here where you begin to kink that cable could actually have an effect, a minor effect in this particular case, but if that kink were greater, as we'll see later on, it could have even more effect. So when we talk about the losses in cables, we talk about it in loss of decibels, which is a logarithmic loss. For our purposes, simple purposes, if you have a 3 dB loss, you've lost half your power. 6 dB loss, you're down to 1/4 of your power, and you can see these other figures. So if you have something that loses 3 dB, you've put out 100 watts from your transmitter, you've lost half that power, you're now at 50 watts. It's important to know cables are going to give you this loss. How much loss are you willing to accept? How much are you willing to spend to avoid that? So what are we talking about? Well, RF, radio frequency, are radio frequencies in the range of 3 kilohertz to 300 gigahertz. Basically, that's 3,000 cycles, or we call them hertz, to 300 billion cycles. Coaxial cables are designed to carry this particular range of frequencies. Now, what are we talking about? We're also talking about the speed of light. Speed of light is measured in meters per second at 299 million meters per second, and we usually round that off to 300 million, or 186,000 miles per second. At a 3,000 hertz frequency, here's a wavelength in feet. 327,000 is a wavelength, 327,857 feet. That's a wavelength. At 300 billion cycles per second, a wavelength is 3/1000th of an inch. And we're going to see why that's significant as we get to the construction of a cable. Okay, electricity is fast, but no matter how fast electricity is, nothing is instant because it will always have to travel some distance. In free space, it's pretty close to the 186,000 miles per second. If it's in something like a cable, it's going to be slowed down. Now let's talk quickly about wires. You're familiar with this kind of a solid wire down the bottom? It's like a household wire. Let's take a typical household wire, 14 gauge. It's rated at 120 volts at 15 amps. It means it can handle 1800 watts because you all remember that the wattage is the current times the voltage. You also have a stranded wire. A stranded wire gives more surface area. And that becomes important, like even in your home, when you attach a light bulb fixture or any other socket, it's usually stranded wire. Why? Because if you attach something here, you're attaching it only to this part and to this part, the tangent of the wire. You're not getting a full-bodied coupling. But when you attach it here, you can see how much more surface area you have. And so you get a better transfer of the current that's flowing through the wire. And we're going to see why this stranded wire is also very important in coaxial cable. Now, when you have current flowing through a wire, there is a magnetic field that is created around it. By the way, a reminder, when we're talking about RF frequencies, we're talking about alternating current, not DC current. Well, this is called the right-hand rule, and it gives you an idea of here's the direction of the flow of the current, but here's your magnetic field going around that line. This is slightly different than what I showed you before, but this is a clamp type ammeter. It doesn't have to touch this wire because around this wire is a magnetic field that's flowing. This is a magnet. It picks up that magnetic field, and that field will cause the magnet to have flow, and that flow can then be measured in this ammeter. Again, a magnetic field is created as you have this flow. Magnetic field is created. It's measurable by something that never has to touch the wire. Now, this is what this electromagnetic field is. It's something that's created by the interaction of the electric field and the magnetic field. If you can see by this diagram, this is at a right angle to the flow. This is at a right angle, and they are at right angles to each other. A better view of that is if you use the left-hand view. And if you take your hand, it's interesting because you can now see three forces that are all at right angles to each other. And this is the forces that are going through, well, these are the forces that are being transmitted in an RF signal. And the question is, what do we do with those forces? Well, we try to use a coaxial cable, which was established first in 1929, first as a means of carrying telephone signals, but then carrying radio signals across the country, because as networks began to grow, it was important to have, let's say, New York and Chicago listening to the same broadcast at the same time, and so cables were used to do that. The basic construction of a coaxial cable is that there's a center conductor. There is an outer conductor called the shield. In between, you need something to insulate it, and that is an insulator. But we're also going to learn that this is called a dielectric material. It does not conduct electricity, but it does allow for charged fields, positives and negatives. And then, of course, there's a jacket protecting it. So what's happening in the coaxial cable? Well, there's resistance. We talked about that in the DC circuit, but that same resistance is in the AC circuit. Now you have this thing called reactance. And reactance is what's happening inside that AC circuit in a capacitor and in an inductance. And we'll talk about that in a few minutes. Conductance is the ability of the particular wire to conduct electricity. And now we have this velocity, which is how fast is the signal going through a wire compared to the speed of light. And we're going to see that cables are rated in terms of how fast. And again, it's an important factor in understanding this. Now let's talk about resistance versus impedance, because resistance is in a DC circuit. It's just in the wire. How much resistance is the wire offering to the flow of electrons? But in AC, you have this addition of the reactance. The capacitor is forced to change with the AC current. It's going from positive to negative. It's being forced to change. The inductor is being forced to change. That adds resistance to the circuit. And that resistance we now call impedance in an AC circuit. So AC circuits will be measured by impedance, 50 ohm impedance, 75 ohm impedance, whereas in a DC circuit, it's just going to be by resistance. Now, what happens in inductive reactance? Well, as you saw kind of in that diagram, in the first thing, you're forcing a change. If you were running and quickly had to change direction, turn exactly in the opposite direction, there'd be a resistance to that change. That's what's happening in an inductor. It's resisting that change. It's measured in ohms, by the way. So here's the formula. And I want to point out in frequency, because I showed you that initially, in inductance, you're multiplying the inductance by the frequency. So as the frequency increases, this number is going to get larger and larger. And you saw what inductance did to the light bulb. It stopped the light bulb from functioning. So this is your inductance, L. This is for the reactance, X. And again, notice that it's going to increase with frequency. And again, it's measured in ohms. When you have capacitive reactance, here's your reactance, here's your capacitance. Notice in this case, it's in the denominator. As you multiply this denominator by the frequency, it's going to get less and less and less. So one thing you'll notice is a relationship between the inductance and the capacitance. You're multiplying the inductance and you're dividing it basically by the same number. So they are working kind of in tangent with one another. And notice again that it's measured in ohms. So now when you're dealing with the impedance, I'll come to a second. Now when you're dealing with the impedance, you are taking the resistance of the wire and the capacitive reactance measured in ohms and the inductive reactance measured in ohms. That will give you your impedance. Now, another thing to notice about electricity traveling down a wire at these high frequencies is that the electrons, which would normally be in this whole wire, well, they don't want to be in the center. There's reasons why, there's physical reasons why, but they start to move to the outside of that wire. And that occurs both here and in the shield. But they move to the outside of this wire. This is called the skin effect. And here's a better idea of it. There's nothing here in the center. These electrons are moving to the outside, and the higher the frequency, the more they're moving to the outside. And if this wire is symbolic of resistance, well, now you've taken away this amount of the wire, which could be handling the flow of current, and you're pushing it into a much smaller area, so the resistance will actually be increasing. That skin effect is a very significant thing when it comes to our RF transfers. So now going back to this wire, understand it is moving, the current is moving to the outside of the wire. A shielded wire will provide much more surface area. And so stranded wires will be able to handle higher frequencies generally than a solid wire. Now, if you don't need the center, then why not eliminate it? And that is the case in many instances. This is called heliax cable. There's no center. There is a cable, there's a center conductor, but this is it because that's where the electrons are going to be. Nothing is going to be here. It's called heliax because of this construction going through the whole cable, and this area will all be filled with some gas. Here is something called hard line, which you may be more familiar with. It's totally surrounded by copper. Here's your insulator, your dielectric material, and again, no center, no reason for it. This is actually a circuit, an electrical circuit presentation of a cable. This is actually what's happening in a cable. Here's the power source. Here's your inductors, which is created in the wire. And here's your capacitors. And ideally, this goes for an infinite length. This will always remain the same. It will always give us some consistency. It's going to be called a characteristic impedance. We're not putting a load on the end of it. We want to make sure that it's consistent so that we get some idea of exactly what's going to happen when we do put a load on it. And what I do want to point out is that there's actually no capacitors, and yet we're showing capacitance. And why is that? By definition, when you have two wires separated by a dielectric material does not allow electricity to pass, but it may allow an electric charge to exist. Air is a dielectric. You don't have electricity passing through air. Other materials are dielectric, as we'll see, but by definition, two wires separated by a dielectric is called a capacitor. So you have through the whole length of a cable a capacitor. Characteristic impedance is the thing that we need to know so that we know what happens if we apply a voltage to a cable. In this characteristic impedance, you can see that it's a function of geometry, but it's a function of everything else that we've already spoken about. And it's, again, independent of line length. No matter what that length is, that characteristic impedance, which is called Z0, should always be the same. The most common characteristic impedances that we deal with are 50 ohm, which is most of our cables, 75 ohm, which is your cable, which is associated in your home, and 93 ohm, which is used in some computers. Bear in mind, a cable could be any characteristic impedance, any characteristic. You're going to create it, and we'll see how it gets created. But we deal mostly with 50 ohm. Why do we deal with 50 ohm as ham radio operators? Well, our two most popular antennas are the ground plane, which again, by a law of physics, has a characteristic impedance of 36 ohms, and a dipole antenna, which again, by laws of physics, has a characteristic of 72 ohms. 50 ohms was somewhere in the middle, and that's why that was selected. How do we know the characteristic impedance? It's a relationship between the outer part of the inner conductor and the inner part of the outer conductor. The outer part of the inner conductor and the inner part of the outer conductor. To go back to something that we've already mentioned, inductance is going to be in this wire. Here's a wire, here's a wire. What's in between? A capacitor. So the characteristic impedance, we're calling it this relationship, but what it is really is a relationship between the inductance in this wire and the capacitance that is in between the two wires. Now, what happens if we change, just to give you some idea? And this is a representation, not an actual perfect representation. Let's say this is our 50 ohm characteristic impedance. Here's our relationship between the outer, the inner, and the capacitance in between. If I increase the size of the center, well, you know from your own home, you go from a 14 gauge to a 12 gauge to a 10 gauge, you have a much greater capacity to handle power. But you're also getting closer to this other wire or shield, and you have less capacitance here. And the possibility is that the inductance could actually cross over and cause a short in your circuit. So they stay away from this kind of a thing when they're dealing with power. I'm sorry, on the other hand, in a 75 ohm, there's much more distance, which is actually creating less capacitance. The further these plates are apart, the less capacitance there is. And for, as we'll see in 75 ohm cable, for your home, for digital use or whatever, it's just much less loss of signal. And that's why 75 ohm. But this is the difference. It's the relationship between the semiconductor, the outer part of the semiconductor, and the inner part of the outer conductor. Now, here you see coaxial cables going from 1/8 of an inch to 1 1/4 inch. What do they all have in common? They're all 50 ohm. Why are they all 50 ohm? Because regardless of the size of the cable, the relationship between the semiconductor and the outer conductor remains in the same proportion. What's the beauty of everything being 50 ohm? That no matter what you have, if it's 50 ohm, it's a seamless connection between the two. Here we have a connector going between roughly I think this is a 7/8 cable into a 50 ohm cable. There's no loss here. The minimal loss, we'll talk about what's called insertion loss, but there's almost no loss here because 50 ohm to 50 ohm, it doesn't matter. So you can connect the thinnest cable to the thickest cable depending upon what your needs are, and you'll have a seamless flow of the RF signal through that cable. Briefly, here's the formula. Again, we pointed out, this is again the formula for characteristic impedance. Again, we just want to point out that it's a relationship of inductance and capacitance, but we measure it and talk about it in terms of that distance between the inner conductor and the outer conductor. Okay, what are the ideal materials for that semiconductor? The silver, gold, copper, copper-clad steel, copper-clad aluminum. Well, how come copper-clad steel and copper-clad aluminum? Well, we talked about the fact that there's no need for a center. Well, if there's no need for a center, if we put steel in there, then we're adding strength to that cable if it's being suspended over a long period, a long distance. If we add aluminum to it, we're adding lightweight material, again, giving it strength, but lightweight material that's less costly than the copper. So these would be the center conductors, the ideal center conductor materials. Now, the insulators, which again, we're calling the dielectric, air, polyethylene, foam polyethylene, and this is my favorite, Teflon. Teflon is capable of handling high heats, and you're going to see it in some of the more expensive conductors. But the actual name for Teflon is polytetrafluoroethylene. Polytetrafluoroethylene. And that is something when you're sitting around at a bar or whatever, and somebody says something, I just throw that name out there, polytetrafluoroethylene, and they're going to look at you and say, wow, this guy's a real genius. Anyway, those are the insulating materials that protect the inner conductor from the outer conductor. Now, the outer conductor is this braid. It's usually copper, copper-clad material, aluminum, and foil. When you look at this cable, you'd be paying a lot of money for this cable. Why is there a braid? Well, this braid is what's keeping that RF energy in the cable and keeping any other interferences outside from not being able to get into that cable. You have braid, you have foil, you have braid. Nothing is getting out of this cable. On the other hand, and I didn't actually notice until last night, this is not actually a coaxial cable. It's actually a shielded, probably audio cable. But look at this braid. Remember we talked about the fact that in that 300 gigahertz wavelength, it's 3,000th of an inch. Well, conceivably, a wavelength of that size could get out of this cable, and that's not what you want to happen. So you're going to pay for braid. If you buy a cheaper cable, it's going to perhaps be more braided like this, and We talk about BRAID in percentages. This is 100% coverage. This might actually be 90% coverage. You're paying for that. And again, it's a reason why you might consider actually paying a little bit more for something. The jacket is important because the jacket, again, it could be made of different materials. Are you burying your cable? If you're burying it, you need something that's going to protect it from water. Is it going to be out in the sun all the time? If so, you need something to protect it from the effects of UV sunlight. And again, there's different things. If you're in a plenum area, if you're in a suspended ceiling in which air is being exchanged, you need to make sure that there's no dangers from the cable, no gases being, coming out of it. So again, jacket. Some of the materials are things that, obviously polyvinyl chloride, you're familiar with, polyethylene, all of these materials. These are all the things that will actually go into the making of the cable. Now let's point out that there is something called non-coaxial cable. We refer to this generally as ladder line. Ladder line is called also balanced line. There's an equal amount of voltage in both of these cables, which does not exist in a coaxial cable where all of the voltage is actually in that center conductor. But if that's the case, where's the dielectric? Well, where's my mouse? Here's the dielectric. This is the dielectric, the combination of air and this material, the same thing over here. And there's a difference in the spacing. So the capacitance has changed between this, which would be the 400, and they call it 450 ladder line, and this one, which is 300 ohm ladder line. So again, that distance is affecting the characteristic impedance. But understand also, while this works very well, this area is now exposed to outside influences, which could be RF from your electric lines, RF from other cables. And so if you're using ladder line, you need to make sure that it is pretty much isolated from any interference, that it doesn't touch any metal, and basically just that it's going to be influenced, and you just need to be careful about it. It's a great line. Lots of people love to use it. Our preference is coaxial cable. Now, coaxial cable loves to go straight. I'm sorry, RF in the coaxial cable loves to go straight, and the same thing applies to the ladder line. It loves to make bends. It's okay with that. There's what's called the bend angle, the bend radius. A bend radius is generally 20 times the diameter of a wire. If a wire is 1/8 of an inch thick, 20 times that is where you safely can bend it without losing any of the RF signal. But as you begin to make different kinds of bends, you begin to get a reflection backwards. And if you ultimately make a right angle, which is what RF does not want to do, you will eventually lose all of your signal. Just want to keep track of time. Okay, so whether you have coaxial cable or whether you have ladder line, you do not want to make a right angle. You will basically shut down your system. Let's take a look at a pretty common cable, RG213. RG stands for radio guide. It's a military specification. Most companies adhere to it if they're bidding on military specs. If they're not, you may find cables having similar names that are very different from one another. But look at the specs of the cable. You would find this for any cable. This, by the way, is what a company put out. And so that's why you have things like 250 feet. That's what they, excuse me, that's what they have in their, that's the cable that they're selling you. But as you look at this, these are the specifications of the cable. In this case, the center conductor of this RG213 is a 13 gauge wire. Well, you already know what a 14 gauge wire is, so you have some idea of how much power that cable is capable of handling. Here's your percentage of braid. Well, first of all, it's a copper braid, and the braid is 96%. Right? Not 100%, but 96%. Here's some more specifications of that cable. And this is what you'd be looking at. It's 50 ohms. Well, that's basically what we're dealing with most of the time. And propagation. Propagation is the speed at which the signal is passing through this cable? 66%, not 100%, not 186,000 miles per second, 66%. It's still very fast. 66% is actually a pretty good number for a cable, but just bear in mind, when that RF signal is going through the cable, there is always going to be loss. In this case, it's going to be slowed down to 66% of the speed of light. Now, this is again, that 13 gauge wire, generally, based upon what we said about 14 gauge, it should handle about 2160 watts. But what happens is, again, we're dealing with not 60 cycles per second, which is what happens in the house, but we're dealing with these higher rates of frequency, which do affect it. Okay, so we want to just, frequency affects the limits of any wire. Now let's see what happens actually in wires. Here's some basic coaxial cables. Look what happens to each of these wires as you go into a higher frequency. You see that you're constantly losing power. This is the maximum number of watts that these cables are able to handle. So even if you take something like the 213, rated at 1800 watts in the HF range, look what happens as the power drops off. I'm sorry, as the frequency increases. So one of the things is that as you buy your cable, what are you going to be doing? Are you going to be doing these higher frequencies? If so, are you going to buy an inexpensive cable? Something like, well, these are all pretty expensive, but something like RG8X is very cheap. Are you prepared to put out 80 watts at 400? Are you prepared to lose, actually, and come down to a maximum capacity of 80 watts at 400 megahertz? But notice, more important is that as you increase in frequency, you begin to lose power, and you remember that in the initial thing that we showed you, as you increase the frequency, you're taking down the power that's actually getting to the light bulb. These are some of our basic cables. No matter what they are, you can see there's loss, but obviously some of these cables have less loss of power. And again, that's what you'll be paying for. Again, we look at the 213 because that's our standard for right now. Okay. When you have loss, again, it's measured in the decibels. Remember that we mentioned that 3 dB is a loss of half your power. Cable loss is measured per 100 feet. That's important to know because if you do 200 feet, you've doubled it. But if you're only running 50 feet, you're taking half of the loss. So for example, if we go back to our RG213 and you look at 400 megahertz, the loss is 4 dBs. You're going to lose a little more than half of your power at 400 megahertz. dB loss per 100 feet. Look at some of the cables, the RG8. I'm sorry, the RG, just lost my finger, the RG8X. Very thin cable, very inexpensive, but look at the losses as you get into these higher frequencies. Would you want that kind of cable there? No, you don't want to be losing 6 dB at 400. Why? 6 dB, remember, is 1/4. So if you're putting out 100 watts, 6 dB is 1/4, you'd be putting 25 watts to your antenna. Do you want to lose that much? No. So if you know that you're going to be at 400 megahertz, you're going to decide on a cable that's going to give you the least amount of power loss. I mean, obviously you don't want this. So you want the least amount of power loss. Again, it's expensive to do this, but you have to decide exactly what you're doing. Now, here's an example of a cable, LMR 1700. Look at the loss in this cable. Limark has, my home club has an antenna going up at 570 feet. If you take the amount of cable necessary, that's 570 feet, another 100 feet or so to get it back to the shack, to the building where the cable is, We're running a 400 megahertz repeater. Look at the loss at 400 megahertz, 0.6 dB. Well, times 700 feet is only a 4.2 dB loss, 4.2, a little more than half our power. We can live with that, but we can't live with putting out 100 watts and getting 2 watts out to the antenna. So here's our LMR. Here's a very expensive cable. This is an 1.25 inch cable. Look at the losses, how limited it is, how good this cable is. And if you can spend retail $20 a foot, then do it. Some people will do that on short runs. But bear in mind, look at the quality of this cable, look at the loss, look at the expense. In some circumstances, you simply have to do it. Okay, so how do you choose the right cable? Frequency of operation, characteristic impedance, power handling, distance to cover, how many feet is it, how many feet are you going to be going, and the flexibility. Now, an interesting thing about cable, just for the heck of it, is the fact that imagine when the spaceships, rockets went out into space. When they're facing the sun, the heat is 180 degrees Fahrenheit. When they turn away from the sun, it's minus 459 degrees Kelvin. Think about that range that a cable has to handle. So as scientists put together all of these things, as engineers put together all these things, they have to remember where it's going to be, what the cable is doing, and basically what they have to do to make it work. All right. When you have a cable, everything that you put into that cable will cause insertion loss. You put a connector in there, you put a meter in there, no matter what you put in there, it's going to cause additional cable loss to whatever the cable itself had as its characteristic impedance. And again, this loss is measured in decibels. Okay, maximum power from your transmitter to the antenna will be obtained when everything in the characteristic impedance is the same. So your transmitter is putting out 50 ohms, your cable is handling 50 ohms, your antenna is designed for 50 ohms. So let's move into the connectors now. Just checking my time. Okay. BNC, this is really what started for me. I said, what is a BNC connector? Now, and if you ask 10 people what a BNC connector is, they don't always know the answer. It's a bayonet Neal-Councilman connector. Paul Neal, Carl Councilman, engineers. Paul Neal developed the N connector, Carl Councilman, the C connector. Their combined technologies became a bayonet Neal-Councilman, and its sister is the threaded Neal-Councilman. Bayonet, threaded. Bayonets are great for quick connects. You've seen them all the time. Not so great for something that's constantly moving around because it's spring loaded. That spring can be affected by the movement, and thus you have a threaded Neal-Councilman, which will give you a tighter connection. Here's an N connector. These are good up to 11 gigahertz of frequency. This is the C connector. This is the, sorry, you can see this, the similarity between the C connector and the BNC connector. Again, BNC common to us, C connector not so common to us. Now, PL259 and SO239, most common to us as ham radio operators. Why is this a PL259? It was the 259th plug in the Army Signal Corps' description of plugs. Why is this an SO239? Because it was the 239th connector in the Army Signal Corps' collection of connectors. Now that can vary also. It could be a different number in the Navy or in the Air Force. It depends on what their specs are. What I want to point out in this picture quickly, we're talking about the relationship here between the inner conductor and the outer conductor. In order to accept this plug, this being the correct characteristic impedance, in order to accept this plug, you need this bump out. This bump out actually changes the distance between the inner conductor and the outer conductor. Here's the inner conductor, but this has now changed it. So for your information, a PL259, which we rate at 50 ohms, is actually, now what do we say? If you increase the distance, it's going to be less characteristic impedance. For your information, a PL259 and an SO239 are generally actually somewhere in the 40 ohm characteristic impedance, 40, 42 ohm, something in that area. These are generally considered good up to 300 megahertz. They're actually called the UHF connector, but very often it's better to change your connections. A very popular connector right now is the SMA connector. This is on a lot of your HTs. Notice how high it can go in frequency, 18 gigahertz. The reason is that there's a lot of Teflon in here. You would not put a lot of voltage through here. It's a small connector, but it can certainly handle very high frequencies. SMA sub-miniature A assembly. Here's an assortment of some various connectors that you're familiar with. Here's an adapter for just about everything. You can go from anything to anything. And here's a recreation, not a perfect recreation, of something that I did during Hurricane Sandy. I had to go from my HT, or I wanted to go from my HT to my outside antenna, because now a minimal amount of power would give me a pretty good signal going into my antenna. I connected, and again, it's not the correct representation, but I connected from an SMA to, in this case, it's a BNC, but I should have been to a SO239. All of these connectors together made very little difference in my signal because each of these connectors only represents 0.02 dB loss. So sometimes I'm concerned, I don't want to put a connector, the minimal loss, it's a minimal loss, don't worry about it. Do what you have to do to get the connection. In this case, all of these connectors had very minimal effect on what was actually going out to my antenna. Okay, look at these capabilities of some of our various connectors. The PL259, this 1800 watts is really at the lower end of the spectrum in the HF range. As you get into these higher ranges, you need different kinds of connectors. Why? Because they can't handle the heat that's created by the, I should have pointed out earlier, when you get to that skin effect, you have all of those electrons flowing into one area, creating tremendous amount of heat. If you don't have the right connector, you can actually melt the material. And it's not unusual, particularly for a PL259 in the wrong frequency range, for the PL259 to melt to the SO239. But you can see, Peter, was that a warning?
Roger that, 5 minutes to go.
Okay, but you can see that as you get into these higher frequencies, change your connector. Some people tell you as you do a wire, get right into an end connector. Okay, right angle connectors, it's not really a right angle. There's a wire in here that's making a very gentle bend because that's what the RF connector, that's what the RF really wants to know. How to choose the right connector, look at all these conditions. Always cost. Cost is always a factor, but if you buy a cheap connector, you're going to get what you pay for. But the frequency, very important. If you know you're going to be in the higher frequencies, do it correctly. All right, an example of the power loss. If you have 100 watts and you lose 3 dBs, that's 50 watts. 100 watts, 6 dB, 25 watts, 100 watts, a 10 dB loss. You're putting out 10 watts. How much are you willing to lose as you go from your transmitter to your, hey, that was pretty good, Peter. You go from your transmitter to your antenna. So since I have 2 seconds left, how do you know what the dB is? Well, there's formulas for it, but in loss, a dB loss is approximately 20% of each dB. So if you have 100 watts and you have a 1 dB loss, that's a 20% loss, that's 80 watts. Now, if you have another dB loss, it's 20% of the 80, which is 16 watts coming off, brings it down to 64. And if you have another dB loss, which would bring it to a 3 dB loss, it's another 20% of the 64, which is roughly 13, which is roughly 51, which is close enough to our 50. So it's just a rule of thumb, 20% per dB, but not 20% of the original, 20% of the resultant frequency. Okay, I guess with that, I can end it. K2KNB at arrl.net if you have any questions. The simulations are from PHET, which is a part of the Colorado University Educational Department. There are great simulations if you have kids. There are great learning simulations there. Mathematics, physics, science, everything that you'd want. And it's a freebie.
Richie, thank
Okay.
you. Thank you very much. I say interesting, informative, but Jose Berrios says, this presentation was very informative. Thank you very much for explaining the facts so clearly. WB2BWU. My words exactly. Great job, Richie. Thank you.
All right. Thank you, Peter.
73s.